Right, we're going to have a look at what happens in series and parallel circuits with regards to the current, the potential difference, and the resistance in these different types of circuits. So in a series circuit, just to refresh our memories, a series circuit has a power supply and it will maybe have, so we're going to put two resistors in here, two fixed resistors. So the DC current has one way through which it can flow through these two resistors. The difference between that and a parallel circuit has many different ways that the current can flow through. So in this case, we've got two resistors. So the current can either go through the top resistor here or the bottom resistor here. It's got two paths that it can go through as it leaves the cell from the positive side. What often crops up with these is calculations to do with Ohm's law. So Ohm's law tells us that if we divide the potential difference around a component, so let's say if I stick a voltmeter on here, and I know the current from reading it from the ammeter here, I can use that to work out the resistance of this component. So let's have a look at how potential difference, current, and resistance behave in these circuits. So here we have a series circuit over here, and I'm going to give this a random value. Let's go for 12 volts. Okay. Now, I'm just going to make up some values here, and then we're going to try and work out the effects. So here, there's going to be, let's go for 8 volts here. Now, this is a series circuit, and the voltage is essentially how much energy per charge leaves the cell, okay? So what I do in my head is I picture these little electrons as they go around the cell, go around the circuit, and each one of them is carrying 12 joules, or 12 bits of energy. Now, in reality, 1 coulomb of charge, if you remember, voltage equals the energy transferred or work done per charge. 1 coulomb of charge is actually billions of electrons, but for simplicity's sake, we'll just say it's 1 electron here. So it's carrying 12 volts of energy. So this energy is transferred here, and we've got 8 volts, so we can't violate the law of conservation of energy. So if we started off with 12 volts, this energy must have been dissipated in the circuit. So we have 4 volts here. Now, that means all that electrical energy is distributed in this variable resistor and this bulb here. So the potential difference in a series circuit is shared between the components. The current is an interesting one. We know that these both have the same, these both have a resistance, I should say. So if we want to figure out what the resistance is, you would need to know the current. And in a series circuit, the current is the same at any point. Okay, seems to be doing a bit funny there. So there is 2 amps of current. So no matter where you observe the current in a series circuit, you should get the same value. Okay, so the current is the same at all points on a series circuit. Now, the resistance, so I picture these little electrons as playing a game of rugby, and they're going through here, and they're going to have to fight their way through a little bit of resistance here, and then a resistance here. So the total resistance of the series circuit is equivalent to the resistance of this first component here, which is a variable resistor, and the resistance of the second component here, which is a bulb. So if there was another component in there, you would just simply add on R3 plus R4, all that sort of stuff. So it's the total resistance there. Now here, if you want to work out the resistance of R1, you would do the voltage, which is 4 volts, divided by the current, which is 2, giving a resistance of 2 ohms. Okay. Now, with the second one here, we have a resistance of a voltage of 6 volts divided by a current of 2 amps, which means we have 8 divided by 2, that is 4 ohms. So the total resistance of the circuit would be an RT of 6 ohms. Okay? Now, let's have a look at this parallel circuit. We've got a 12 volt supply voltage. So each little electron that's leaving this way from the cell is going to be carrying 12 joules per coulomb of charge. All right? So the electrons have two ways to go. They can go this way, or they can go this way. And if we assume that both these bulbs have the same resistance, then electricity will usually take the path of least resistance, but in this case there's no difference, so the current in both ways will be the same. So each electron will go this way, or it will go this way, and it will still be carrying 12 joules per coulomb. So the voltage in a parallel circuit is shared between the branches of the parallel circuit. So we've still got 12 volts being carried by that electron or unit charge, and 12 volts carried by this unit of charge. So if we know the resistance of the bulb, we can work out the current at the different points. So the voltage is the same in each branch of the parallel circuit. Okay, I'm having trouble writing this for some reason. Let's try that again. It's the same for each branch. Could be my spelling, could be my ability to write. Either way, they're both pretty awful. Anyhow, now the current, I mean, you can see what's going to be happening here. This, imagine people walking down a corridor. They can either go down here, or they can go down this route here. Now, to work out the current here, we would have the voltage divided by the resistance, because I equals V over R, and both values will be the same on both of these branches. So we have 12 divided by 4. That gives us 3 amps in this branch of the circuit here. This value will be exactly the same, because we've got 3 amps going this way, 3 amps going this way. So if 3 amps comes up here, 3 amps comes along here, you're going to have a total of 6 amps here. Thus making sure we don't lose any electrons down the back of the couch. We're conserving charge as both the 3 people walking this way, the 3 people walking this way, both converge to give us 6 amps here. That 6 amps will flow through the cell. We'll still have 6 amps here, until it splits up once more to go one of either of those routes. Now, regarding the resistance, there is a law for resistors in parallel which you will learn in A-level physics. It's 1 over R1 plus 1 over R2 plus 1 over, if there's another one, R3. Now, I'm fairly sure, you definitely don't need to know this for combined. I forget off the top of my head if you need to know it for GCSE physics. But effectively, the easy way to remember this is the total resistance, oh, forgot 1 there, 1 over RT equals 1 over R1 plus 1 over R2. Basically the total resistance of this entire circuit, this entire parallel circuit, will be lower than the value of the lowest resistance. So the total resistance here would be less than 4 ohms. Okay. So to summarize, in a series circuit, if you can remember one of these, you can remember the other ones. It's pretty straightforward. It's just reversing what's going on. So in a series circuit, the current is the same at all points in the circuit. The voltage is shared between the components of the circuit. The voltage in a parallel circuit is the same for each branch of the circuit. So if this is 6 volts here, it'll be 6 volts across every single one of these resistors. Whereas the current is shared according to the resistance here. So if you were an electron, you're going to find it much easier flowing through here and here rather than this 20 ohms resistance. Now, in a series circuit, the total resistance is equal to the sum of all the resistors. So if we have 4 plus 6 plus 3 ohms resistance here, that's going to give us a total of 13 ohms resistance in this circuit. And in this parallel circuit, the resistance here would be lower than the smallest resistance. So it would be lower than 10 ohms. Okay, I hope that helps a little bit.